So now let's understand of another very important property or law in probability called as the law of total probability. To understand this, it's best to look at an example. Actually, this is an example from manufacturing sector, right? This is a very important and a very interesting application of probability to manufacturing sector, right? Like manufacturing bulbs or manufacturing transistors or manufacturing cars, whatever you want to call it as. Okay. Imagine for most companies that are manufacturing, they have multiple factories, right? So imagine I have two factories. Imagine I'm manufacturing bulbs just as a simplicity, but I could be manufacturing cars or whatever you want. Imagine I have two factories. Let's call them X and Y, right? Between these two factories, let's assume I'm manufacturing some bulbs. Okay. So now what happens here is this. Let's assume these two factories are different. The technology that is used in these factories is also different. So this is the first fact given to us. The second fact here is in the bulbs that are made. So in the bulbs made in factory X. So for the bulbs made in factory X, what happens is they survive for or they work. These bulbs work for 5,000 hours, right? Which is a pretty good number. They work for 5,000 hours in 99% of the cases, right? In 99% of the cases, the bulbs made in factory X work for 5,000 hours. Similarly, let's assume bulbs made in factory Y, right, work for 5,000 hours in only 95% of the cases. That's probably because in factory Y, I'm using some older technology to make bulbs, but in factory X, I'm using some newer technology to make the same bulb. Because of the manufacturing processes being different, in factory X, there is a 99% chance that the bulb will survive for 5,000 hours. In factory Y, there is a 95% chance, right? Not bad. Now here comes the question. Now let's assume I'm shipping a package. Okay, I'm constructing a package and I'm shipping it to all the distributors of bulbs, right? Now in this package, what I've done here is I've chosen 60% of the, so let's assume I create a packet like this or a package to be sent to distributors. That's what happens in manufacturing, right? Factories produce something and then they send it to the distributors. The 60% of the bulbs that I have, let's assume, come from factory X, right? And 40% of the bulbs that I ship come from factory Y. Now, when I'm shifting my bulbs, I need to give, because these bulbs look identical. Nobody can say which bulb came from which factory, right? So now, as a manufacturer, I have to give some guarantee, right? So I want to compute the probability that a bulb that I've shipped, has, so I want to give some certainty. I want to give some number like 99% or 95% and say, what is the probability that my bulb works for 5,000 hours, or bulb has a lifetime of at least 5,000 hours. The bulb works for 5,000 hours. Because if I can compute this on this shipment, I can put a sticker and say, these bulbs will work for, let's assume this probability is P. On this case, I can say these bulbs will work for more than 5,000 hours. With let's assume this probability, let's assume is 98%. Let's just say. Then I'll say in 98, there's a 98% chance. Again, this number we don't know, we'll compute it in a while. Let's assume it is 98%. Then I'll say that these bulbs will work for over 5,000 hours in 98% of the cases. Now the big question mark is, how do I compute this probability? Right? It's a very valid problem, right? This is, again, probability and statistics are also used in manufacturing to estimate, and this is a fairly real world problem, right? Most manufacturing, whether you're manufacturing bulbs, you're manufacturing cars, you're manufacturing medicines, whatever you're doing, or whether you manufacture anything that you're manufacturing, since multiple plants will have multiple technologies, you will have to compute this. How do you do this now? Let's try to understand this. Okay, first let's create some events. Okay, so let's create an event A, which says event A is basically the event that a bulb survives, a bulb works. Event that a bulb works for 5,000 hours. Okay, bulb works for 5,000 hours. This is my event. What is my sample space? All the bulbs that are manufactured till now. Look at this. My sample space is the space of all the bulbs. Now each of these bulbs can come either from, again, first let's write this, right? My event A is the set of bulbs, right? Is this event this event basically, like each bulb, manufacturing each bulb is an experiment or an event, right? So of all the bulbs that I have, the set of bulbs that work for $5,000, I can create a set for them. Or the event that I actually generate or manufacture a bulb that works for $5,000, let me call that event A. Now, this whole set S, because look at this, I have only two factories in which I can produce these bulbs, right? So if you think about it logically, this whole set S of bulbs that are made can only come from two sets, right? So this whole set, I can break it into two sets. This whole set, I can break it into two sets. This green part is B1. This green part here is B2, right? Or BY. Let's call it BX and BY. Now, what is BX here? BX basically means, BX is an event that the bulb is made, a bulb is made at factory X, at factory X. So the bulb is made at factory X, right? At X. So similarly, BY is the event that the bulb is made at factory Y, right? Look at this. Any bulb that I make has to be made either in factory X or in factory Y, right? And this A is now, look at this, my whole space S, my space S is BX union BY, and no bulb can be made in both these factories. If you look at it, this set is BX, this rectangle is BX, this rectangle here is BY, which also means BX intersection BY is a null set. Okay, this is very important. Okay, this is an important observation, because a bulb is either made in X or in Y. There is no bulb which is made in both of them. And every bulb has to be made either in X or in Y. Now look at my A now. A is the event that a bulb works for $5,000. Now how can I rewrite A now? How can I compute probability of A? Can I write probability of A as, because this A, see, my A, part of A can either belong to BX. Look at this. This A is inside BX. This part, this highlighted part, right? Similarly, this highlighted, this blue part is inside BY. So can I write probability of A as probability of A intersection BX, which is this white part, plus probability of A intersection BY, which is this blue part, right? This is very simple, right? Again, look at this. This part and this part are disjoint. They're mutually exclusive. Because what does this say? This says that I have a bulb that is made in factory X, and it works for $5,000. This is basically a bulb that is made in Y and works for $5,000. Right? I hope you understood this, right? Now, how can I write this? Again, simple conditional probability. How can I write this? Probability of A given BX divided by probability of BX. This is intersection, right? So multiplied by, this is intersection, right? Multiplied by probability of BX plus probability of A intersection A given BY multiplied by probability of BY. Now what is given to us? Look at the data that is given to us. Bulbs that are made in X, that are made in factory X, work for 99% of the cases, which means given a bulb that is made in factory X, what is the probability, what is the chance that it works for 5,000 hours? This is already given to us. This is nothing but 99%. This is given to us, right? This is 99%. So this is nothing but 0.99 multiplied by, what is the probability of BX? In my case that I built, in my shipment that I built, what is the probability that an item here belongs to X? Or a bulb that is here is made at factory X? 60% chance, right? So 0.99 into 0.6 plus, what is the probability that given a bulb that is made in factory Y, what is the probability it survives for 5,000 hours? This is given to me as 95%. So this is nothing but 0.95 into, in my shipment which I constructed, 40% of them come from factory Y, into 0.4. That's it. This gives me the answer, right? This is called the law of total probability, because I can compute the probability of A as the sum or as the total of these two probabilities. Again, remember here that my universe of all the possibilities or my sample space is a union of these two probabilities, these two events, and these two events are disjoint, right? Very simple example. Now from this example, we can generalize the whole thing. I can say, imagine if I have a sample space S like this, which consists of multiple disjoint BIs. Look at this. Imagine I have multiple BIs. This is B1, this is B2, this is B3, this is B4, so on and so forth, right? Now here, the condition that it has to satisfy here is that each of these BIs, okay, just like here, again, I'm trying to, here we have taken an example and understood this concept of the law of total probability. Now I'm writing a mathematical equation for that, right? So it says, if I have these B1, B2, if I have B1, B2, B3, so on and so forth as events such that BI intersection BJ is a null set, which means that they're mutually exclusive. This basically implies that each of these, every pair here are mutually exclusive. That is important. And at the same time, B1 union B2 union B3 union so on and so forth equals to my whole sample space itself, which means my sample space can be broken down as union of disjoint sets. Then if this is the case, then any event you take, pick any event here. If this is my event A, then any event A, the probability of any event A can be written as probability of A intersection B1 plus probability of A intersection B2. Again, I'm able to add this because these are mutually exclusive events, right? Plus probability of A intersection B3, so on and so forth. If A does not intersect with some B, right, you don't have that intersection here. That's it. So this again, I can further write it as probability of A intersection B1 A given B1 multiplied by probability of B1 plus probability of A given B2 multiplied by probability of B2, and so on and so forth. So this you can write it as summation over I probability of A given BI into probability of BI. This is what your law of total probability says. It says, given a sample space S, if you can construct mutually disjoint sets BIs such that the union of them is equal to S. So what does this mean? This means mutually exhaustive. Okay, so this is what is called as an exhaustive set. So these types of sets are called mutually exclusive and exhaustive. Okay, so they're called as mutually exclusive because their intersection is a null set, and they're also called as exhaustive because their union equals to the whole sample space, right? So these types of sets are called mutually exclusive and exhaustive, right? If you have these sets BIs, B1, B2, B3, so on and so forth, which are mutually exclusive and exhaustive, then the probability of any event A, which belongs to this sample space, any event A can be written as summation over A conditioned on BI multiplied by probability of BI. And this is exactly what we have used here. In the case of the manufacturing example, where I had two factories, this is exactly the same thing that I have done, where instead of multiple BIs, I just had B1 and B2. That's a very simple example, very useful property, especially in examples like these.